Maxwell's equations. So we have Maxwell's equations in integral and differential form. These are the integral forms of Maxwell's equations. These govern all of electricity and magnetism in a vacuum. We don't cover E and M in materials here in this class. A higher level version of this class would cover that. Here's Gauss's law. This says that electric fields are caused by charges. This is equivalent to del dot E equals rho over epsilon naught. That's the differential form. And that says the source of electrical fields are charges. Positive charges are sources. Negative charges are sinks. This says that electric fields lines start at positives and ends at negatives. Gauss's law for magnetic fields says that the definite integral of B dot dA, the magnetic flux through any closed surface, is always 0. And that's because there's no such thing as a magnetic charge. This in differential form says del dot B equals 0. That's equivalent to saying that B is a curl of some conservative vector field. So there's no such thing as magnetic monopoles. There are no magnetic charges. This is equivalent to saying magnetic field lines never start or end. They're all loops. We have Faraday's law that says a changing magnetic field creates an electric field. And then we have Ampere's law. Now your book doesn't really go into Ampere's law. Normally we would spend a week on Ampere's law, but your book barely covers it at all. So I'm not going to do that this semester. This is our first time using this book. But this says that currents create magnetic fields. So all of this together says moving charges create magnetic fields. Changing magnetic fields create electric fields. So there's this symbiotic relationship between E and B. Electric fields are caused just by charges. If I have just a charge sitting in the universe, all I have, this is my entire universe, just a charge sitting still. I'll get an electric field that points away from that. I'll get an E, but no B. Moving charges, changing electric fields create B. So now I take this charge and I move it at some constant velocity. That would create a constant B. So of course we still have an E. We have a changing E, which creates a constant B. Now what if we go up a level? So that's stationary charge, moving charge. What if I have some charge accelerating? What if I take this guy and I move it back and forth and back and forth? So I'm accelerating, I'm changing its velocity. Accelerating charges create changing magnetic fields, which then induce new changing electric fields. This is how we get electromagnetic waves. If I were to do this with a charge, that would emit light. That's what light is, an electromagnetic wave. This is how we emit light. We have accelerating charges. That's all light is an electromagnetic wave caused by an accelerating charge.